So, Samuel, we've established tensors are key. Now, how do we turn real-world stuff, videos, text, etc., into tensors suitable for deep learning?
Right, Alfred. It's about representation. We need a way to translate data into numerical arrays a neural network can understand.
Like, how do we convert a video into a tensor?
We break it down. Think pixels. Each pixel has color values. We turn those values into numbers. A video's a series of images. Each image is a 2D array of pixel values. That's a tensor.
So, a video is a 3D tensor? Because of time?
Exactly. The third dimension represents time. The other two represent width and height of the image.
And text? How do we make words into numbers?
That's more complex. We use techniques like word embeddings. Essentially, we create a numerical representation for each word. It's like a dictionary mapping words to vectors.
And that's what allows the model to understand context, right?
Yeah, that's where the magic happens. Models can then see relationships between words, analyze grammar, meaning, and so on.
So, these datasets, images, volumes, tables are crucial for training, right?
Absolutely. We need them to demonstrate how our models learn and handle different kinds of data.
How do we know if the representation is accurate or appropriate?
Trial and error, usually. You have to experiment with different embedding techniques, data pre-processing steps, and consider the model architecture itself. It's about finding a representation that reflects the structure of the data and works well with the specific model you're using.
Good point. What's the importance of loading data from common formats?
Makes it easy to work with real-world datasets. Pre-formatted formats like CSV or image files are common and ready to use.
So, we can get the format right and then load it in? Easy peasy?
Not quite. Raw data often needs adjustments. Maybe we need to normalize image intensities or handle missing values in a table. It's about making the data suitable for the model.
Interesting. And what if the data isn't perfect for the problem?
We use tensor operations. We can manipulate data, scaling, shifting, etc., to make it fit the model.
That's a lot to consider. Sounds like we need to get hands-on practice.
Absolutely. The examples will really solidify your understanding. Each data type, from images to text, will come with its own dataset.
Excellent. That sounds super practical. Let's jump into the image data. We'll learn how to work with them. Then we can scale up.
Sounds good. Let's do it.
So, Samuel, you were talking about image data. How do these images get turned into something a computer can understand?
Yeah, Alfred. It's all about transforming those pixel grids into numerical representations. Think of an image as a grid, right? Each grid point, a pixel, holds values.
Right, like a little tiny square.
Exactly. And those values can represent different things. A grayscale image, just one value per pixel. Color images, multiple values, usually 3, red, green, and blue, that combine to create the colors we see.
So, if you had a red pixel, it'd be like a code for red, right?
Precisely. And sometimes, these values aren't just simple numbers. They might be 8-bit integers, typical for consumer cameras. But in medical industrial applications, we might see 12 or 16 bits. That provides much greater precision. Think about it, bone density, temperature, even depth from a sensor, that needs more range of values.
So, basically, the complexity increases with the number of bits, and with the information each pixel needs to convey, right? How does PyTorch expect this data?
PyTorch, like other deep learning frameworks, wants the data in tensors. This just means arranging these pixel values in a structured way. It's essentially a multi-dimensional array, and the image becomes a 3-dimensional array, width, height, and depth. Depth referring to the number of channels.
A 3-dimensional array. That's a good way to visualize that. So, 8-bit versus 16-bit affects the range of values a pixel can take. What are the implications for applications?
Huge. With 16-bit, you get far more subtle variations. Imagine trying to recognize subtle differences in medical images. Those extra bits can matter. You can discern tiny variations in bone density or blood flow.
And 8-bit just isn't enough for those kinds of applications?
Well, it's absolutely fine for many tasks, like recognizing cats in pictures or identifying objects. But you see limitations when you want precise details.
So, more bits allow for much greater detail.
Exactly. More data points per pixel result in a more detailed model for computers to work with.
So, Samuel, you're saying colors can be broken down into numbers?
Exactly. RGB, red, green, blue. Think of it like mixing paints.
Okay. So, each color has a value?
Yep, a value for red, green, and blue. Higher values mean more intense color.
And these channels you mentioned, what are they?
Each channel, red, green, or blue, is like a grayscale image showing only that color.
Like a filter?
Precisely. Imagine looking through a pair of red sunglasses. You'd only see the red parts of the scene. That's essentially what a red channel is doing.
So, the rainbow in figure 4.1. The red part shows up strongest in the red channel?
Right. The red band is brightest in the red channel. The blue channel picks up the blue parts of the rainbow, plus the sky.
Interesting. So, white is high in all channels?
Yes. White light contains all colors. So it'll show up brightly in all 3 channels.
Cool. Is there a practical application for this?
Absolutely. In image processing, you can adjust individual colors by tweaking the channel values.
So, if I wanted to isolate the blue part of a picture, I could do that?
That's right. You could adjust the red and green channels to 0.
Makes sense. So the way color is digitally encoded influences how we analyze images.
It really does. And it's fundamental to many image manipulation and analysis techniques.
Okay, Samuel, we're talking image loading now. So, Imagio, right? Why use it?
Yeah, Imagio's great for handling different image formats. It's got a consistent way to load them.
So, like JPG, PNG, GIF?
Exactly. It's good for lots of image types. And it outputs a number py array, which is useful.
A number py array? What's that, exactly?
Think of it as a grid of numbers. Each number represents a pixel's color value. Number py makes it easy to work with these grids.
And this Bobby.jpg image?
Yeah, it gets turned into this grid of numbers. 3 dimensions, right? Width, height, and red, green, blue values.
So, 3 numbers per pixel. RGB, you mean?
RGB, exactly. Very handy, for sure. It's like a numerical snapshot of the image.
Wait, so if we get a number py array, why not just use it directly with PyTorch?
Well, PyTorch needs images in a specific format: channels, height, width. That's C, H, W.
Channels first? So, red, green, blue, then width, then height?
Right. The Imagio number py array needs to be reshaped, basically.
Makes sense. You're saying PyTorch, it has a particular order.
Yep. It expects that format for processing images, like training neural networks.
So, the Imagio is just a tool to get the image into a format that PyTorch can use? Makes sense.
Exactly. It's about getting the data right before you feed it into PyTorch models. A crucial step.
Interesting. And why is it crucial to have data in the right format?
Because PyTorch modules are designed to expect the data in that specific structure, or they'll probably break down.
So, a mismatch there, and your calculations could be all wrong?
Potentially. It's like putting the ingredients into a recipe in the wrong order. You don't get the right outcome.
Okay, Samuel, so we're talking image data now. We've got these images, and you're showing us how to put them into a format our neural networks can understand.
Yeah, exactly. We need a structured way to handle multiple images.
So, this permute method, what's its deal?
It rearranges the image data. Imagine a picture. Channels are like layers of colors: red, green, blue. Permuting them, well, it's like shifting those layers to a new order to make the data flow nicely through our system.
So, it's not making new image data?
Nope, it's just changing how the computer sees the image structure in memory. Think of it like looking at a photo from a different angle. It's the same photo, just arranged differently. It saves memory and speed.
Makes sense. And why is this channel 2, 0, 1?
Well, it puts the color channel first, and then the height and width. It's a common approach in deep learning, to have the channel dimension first, then height, then width. And this specific order allows for optimal processing later.
Got it. What about this batch creation stuff?
We're now dealing with groups of images. We want to have them in a neat batch to feed to our network.
So, what's the pre-allocation trick?
Instead of adding images one by one, we create a big empty space, like a container, sized to hold our images. Then, we just fill that space with our images.
So, efficiency-wise?
Definitely. It's much faster than adding images one by one. It's like filling a bathtub. It's faster to fill it all at once than to drip water in.
And the U8, what does that mean for the data type?
We're using an 8-bit integer for each color value. Standard for images from cameras. Our network expects this.
You're explaining, as always, how important data format is for the deep learning model. So, you're dealing with PNGs now and selecting the RGB portion?
Yeah, often images have an extra alpha channel for transparency. But for our network, we only care about red, green, and blue. So we grab just those 3 channels.
Gotcha. Could you give an example? If you wanted more images?
Just increase the batch size. More images would simply fill the container.
What about if there are errors in the image paths?
We could have error handling in place. Our program should check if those images are present and properly formatted. If not, we'd have to skip them, or add some feedback telling us what went wrong.
Okay. Samuel, we're talking about prepping data for neural networks. So, you're saying normalization is key?
Absolutely. Neural networks love data in a specific range.
Like, what's the ideal range?
Often 0 to 1, or -1 to 1. Think of it like a standard scale. Makes the training more efficient.
So, how do we get data into that range?
Well, one simple way is to divide by the maximum value. Like if your pixels are 0 to 255, divide them by 255.
That seems straightforward. But wait, what if the data isn't all in the same range?
You're right, Alfred. That's where calculating mean and standard deviation comes in. You find the average and spread of the data.
So, you're standardizing it?
Yeah, standardizing each channel. Then you adjust each data point to have a mean of 0 and a standard deviation of 1.
Okay, so, why do we do it by channel?
Different color channels in images, for example, might have wildly different ranges.
So, for one image, we're normalizing pixel values separately per color channel?
Precisely. Makes sure the network processes each color similarly.
And it's not just about images, right?
No, this normalization method works with any type of input, as long as we have a good understanding of its distribution.
But why compute mean/STD per batch initially?
You're onto something. Ideally, we compute mean/STD across the entire training dataset. Pre-calculated values are more robust and efficient.
So, a batch is just a small portion?
Right, batch is a sample subset. Calculating mean/STD from just one batch is less precise. Learning from the entire training dataset is optimal.
So, what if we don't have the whole dataset?
It's less accurate, but you can use batch-level normalization as a good starting point.
Okay, that makes sense. So, we normalize data to a specific range to help the network. Any other tricks to make data more useful for the network?
Absolutely. There are geometric transformations, like rotations, resizing, and cropping images. They enhance training data variety.
That's good to know. So, data preparation isn't just one method, it's a whole strategy.
Exactly. It's a crucial iterative process to help networks learn faster.
So, Samuel, we're talking about 3D images now. Can you explain how these volumetric datasets differ from 2D images?
Sure, Alfred. 2D images, like photos, show us a flat slice. But volumetric data, like from a CT scan, stacks those 2D slices together.
So a whole body?
Precisely. Imagine slicing a loaf of bread. Each slice is a 2D image. A CT scan is like having all those slices stacked to show the entire loaf.
Interesting. And what does intensity represent in these 3D image datasets?
Intensity, in a CT scan, shows density. Different tissues, like bone, lung, or fat, have different densities. The scanner measures the X-ray absorption. Higher absorption means brighter intensity in the image.
So, darker means less dense?
Exactly. Darker shades represent things like air, lungs, and lighter shades represent denser things like bone. It's like a visual map of the body's internal structure.
Makes sense. How does this relate to the idea of a tensor?
Well, we represent this 3D information as a tensor. Think of it as a 3D array, but instead of just a width and height, we have depth too.
So, it's like a cube?
Exactly. And that depth dimension is the stacking of those 2D slices. We usually store this in a tensor.
And why is it 5D sometimes?
Good question, Alfred. You see, we also have channels, like intensity. Sometimes it's a single channel, so we often omit that dimension and have a 3D tensor. But in more complicated cases with color, it could be NX, CX, DX, HXW. That extra depth dimension N represents the number of scans or slices, and CX, DX, HXW represents the volume, spatial structure, and channel info if needed.
So, a 5D tensor is when we've got additional information beyond just the 3D shape, like maybe different types of imaging?
Correct. The extra dimensions are just more information about the data.
Can you give a counterexample?
A simple photo of a flower wouldn't be volumetric data. It's 2D, not a stack of slices. A picture of the flower, with its color, would have the channel dimension.
So, it's a fundamental shift from thinking about 2D photos to thinking about 3D structures. We're not just looking at a flat surface, but at a volume. All right, Samuel, we're diving into loading CT scans. So, this volread function, tell us about it.
Yeah, it's a handy tool for grabbing a whole bunch of medical images, like CT scans. Imagine a stack of pictures, and it gathers all those DICOM files.
DICOM files? What are those?
Digital imaging and communications in medicine files. They're the standard way to store medical images. Think of it like a universal format for these pictures.
So, volread pulls them together into a 3D array? That makes sense. Why is a 3D array better than other ways of organizing this data?
Well, it's efficient. You can easily analyze the volume by looking at individual slices, and all the math operations you need to do with the scans work seamlessly, with the data neatly lined up, kind of like a well-organized stack of papers.
Got it. And what about this NumPy thing?
NumPy is a Python library. It creates really powerful ways of managing numerical data. It's excellent for handling those 3D arrays with lots of numbers quickly and efficiently.
Okay, so we have this 3D array, but then we're converting it to PyTorch. Why the conversion?
PyTorch is a library super popular with deep learning. It's like a specialized tool for our kind of work. So we transform the data to be compatible with PyTorch.
So why is there the unsqueeze step?
Because PyTorch expects data to have a certain layout. It's a specific format that's needed to do the deep learning work properly. The unsqueeze step, it adds a dimension, essentially creating the necessary structure for the PyTorch library to recognize and use the data effectively.
So, it's like preparing the data for the next deep learning step?
Exactly. We're putting the data in a format the PyTorch model can interpret. We do this to make sure our deep learning model can handle the data properly.
How important is that structure step for deep learning? What would happen if we skipped it?
The model won't be able to process the data correctly. It might generate errors, wrong predictions, and the output might be very wrong. Essentially, the model would not function correctly. If the data is not in the correct format, the model can't really understand what it is looking at.
Fascinating. So, we're essentially prepping the data for advanced AI processing.
That's right. This is one of the first stages. We prepare the data for use. Then we can potentially create a 5-dimensional dataset for more complex analysis with multiple volumes.
Makes perfect sense. So we're building blocks towards a complex model. That's great.
Precisely. We're preparing for more advanced data and AI tasks, like working with multiple CT scans at once.
So, Samuel, you're saying tabular data is like a spreadsheet, right?
Exactly. Think of a database or a CSV file. Rows are samples, and columns.
Hold different info about each sample, like temperature and color?
Yeah, it's a mix of data types. Numerical values, labels, everything.
But why is this important? Why is this data special?
Well, it's common. Lots of data is in that format. But crucially, it's not like time series data. We don't assume order matters in a table.
So, what's the difference then?
In time series, samples are related. A stock's price today depends on yesterday's. Not the case with a table of apple weights and colors. They are independent.
Okay, that makes sense. And you mentioned homogeneity.
PyTorch tensors, they're different. Everything's numbers. Neural networks need numbers, see?
Why numbers? Why not labels?
Because neural networks operate mathematically. They do matrix multiplications, apply functions. They need consistent numerical inputs. You need to convert labels into numbers, like encoding blue as a specific numerical value, or an array/vector of values. Otherwise, they're useless.
So, it's a crucial step to get the data in that numerical format for processing in neural networks?
Absolutely. Conversion is a key step. It's all about getting the data into a format suitable for the model. Otherwise, we can't utilize the power of neural networks.
So, troubleshooting? What are common problems in handling this kind of data?
One issue is when the columns have different scales, like temperature measured in Celsius and weight in kilograms. Feature scaling or normalization is needed. Also, handling missing data is a critical task. Different strategies are available, imputation, or removal depending on the data and model.
So, Samuel, we're diving into wine data now. Real-world datasets, huh?
Yeah, Alfred. Crucial step. We need to transform real-world stuff, like wine characteristics, into a format a neural network can use. That means encoding it into numbers.
Okay, so we've got a wine dataset. What's special about this one?
It's got sensory quality scores. Crucially, this data links chemical properties, like acidity and sugar levels, to a taste score. Imagine, Alfred, predicting how a wine will taste just from its chemistry.
Fascinating. And what's the task here?
We want to see if we can predict the quality score from the chemical info alone. Pretty cool.
But why sulfur? The image shows a link between sulfur and quality.
Exactly. The graph suggests a correlation. We're hoping to see a quality increase as the sulfur content drops. So, potentially, there's a negative correlation there. But real-world datasets aren't always so clean. A dataset might show a trend, but more often than not, it is more complex than a single variable relationship.
So, we're looking for that relationship. Why is this important?
Understanding this connection could help winemakers. They might adjust their sulfur dioxide use to improve quality, you know? It's a practical application, not just a theoretical exercise.
Right? That makes sense. This dataset also gives us a basic idea of what's in it. What's the structure?
It's a CSV file with 12 columns. The first 11 are chemical measures, and the last is the quality score, from 0 to 10. Pretty straightforward, you know?
How do we start working with it in a deep learning context?
Well, we'd need to prepare this data, making sure it's in the right format for our network. Data pre-processing is key, you know. Normalization, handling missing values, these are all essential steps.
So, Samuel, we're loading this wine data. Seems straightforward enough. But why number PY? Why not just use pandas?
Yeah, pandas is great, but NumPy's quicker for this. Plus, PyTorch plays super well with number PY arrays. It's more efficient memory-wise, especially for larger datasets. Think about it, we don't need the full pandas ecosystem here.
Gotcha. So, this number PY array, what's it actually doing?
It's a grid of numbers, representing our wine data. See, it's organized by rows. Each row is a wine sample. And columns? Those hold different wine characteristics like acidity, sugar, density, and quality. NumPy's super fast at these numerical operations.
Okay, so we're turning it into a PyTorch tensor? Why?
PyTorch is amazing for deep learning. The tensor is just an optimized array that works really well with PyTorch's functions. It helps with computations, like mathematical operations on the data, really quickly.
So we're moving from numbers in a table to a special array. Helpful?
Hugely. Imagine thousands of wines. Doing calculations directly on the number PY arrays is faster than with pandas data frames. Think of it as a supercharged version for machine learning.
Now, you mentioned quality. Is that a continuous value?
Well, quality is an integer from 1 to 10, or whatever the actual scale is. Not really continuous, more like ordered categories. You could say higher quality wines are better, but not twice as better. It's ordinal.
Interesting. How about something like alcohol content? Continuous?
Definitely continuous. You know, we can measure it with units and it's ordered. If one wine has 13% alcohol and another 14%, we know the difference, and we can do math with those values.
So, these different kinds of numbers matter for how we analyze the data, right?
Exactly. Continuous, ordinal, categorical. They all require different kinds of analysis in machine learning. You can't just average small, medium, and large, for example. You'd get a nonsensical result.
That makes sense. So different types of numerical values impact our analysis. How do we handle different types in our machine learning models?
It depends on the specific model and the tasks you want to perform. We'd need to adapt our methods based on whether the data is continuous, ordinal, or categorical. This is a crucial aspect of data preparation.
Okay, Samuel, so we're talking about representing scores. How do we decide if a score is a continuous variable or a label?
That's a great question, Alfred. It really depends on the nature of the score and what we want to do with it. If the score is something like a temperature reading, or a wine's rating on a scale, treating it as a continuous variable makes sense. We can use it in a regression task to predict some other variable based on that score.
So regression predicts a number, right? Like if we know the chemical analysis, it could predict a wine score?
Exactly. But if the score is something like wine color, red, white, or rose, then it's a categorical label. Treating it as a label in a classification task is the way to go. We want to predict the category based on the chemical analysis.
Got it. So, it's all about the data type. And that's why we separate the score from the input tensor?
Precisely. Keeping the score separate allows us to use it as the ground truth for our model without letting it influence the model's internal calculations.
Interesting. Can you give us a concrete example in the wine context? So we have a data point in the input. What will we do with that score?
Well, let's imagine the input represents the chemical composition, like acidity, sugar content, etc. If the score is a continuous rating from 1 to 10, we'd keep it separate and use it in a regression task. If it's a label like good, bad, or okay, we'd assign each label a corresponding integer in a classification task.
How does that process translate into code?
The code snippet selects the target column, which contains the scores, keeping it separate from our input tensor. Then, to change it to integer-based labels, we can convert it to long format.
So we take this continuous score and essentially make it a discrete category. Makes sense. What are some common pitfalls to watch out for?
One common pitfall is forgetting to separate the target, the score, from the input tensor. This can lead to your model overfitting on the score itself. Also, if the score isn't truly continuous or categorical, the model might not perform accurately. It's crucial that the data type of the score corresponds to the task, be it regression or classification.
Great explanation, Samuel. So, this separation is key for accurate model training. Thanks. Okay, Samuel, we're talking about one-hot encoding. Can you give us the gist of it?
Sure. One-hot encoding takes numerical scores, like wine quality ratings, and converts them into a format a machine learning model can better understand.
So, it's not just about the number, but also how it's represented?
Exactly. Instead of just the raw score, you create a vector. Each position in the vector corresponds to a possible score.
And how does that work?
Let's say you have scores from 1 to 10. You make a 10-element vector. For a score of 5, you put a 1 at position 5, and all other positions are 0.
So, a score of 1 would be all zeros, except for 1 in the first position?
Right. 1 0 0 0 0 0 0 0 0 0, and a score of 10 would be 0 0 0 0 0 0 0 0 0 1.
Okay, that makes sense. What's the advantage of this?
Well, it turns a continuous variable into a discrete one. If the scores have a natural order, like wine quality, the order is preserved. But if they're more like types of grapes, where there's no real ordering, one-hot is better. You see, in these cases, the difference between scores 1 and 3 might be meaningful, but the same score is not necessarily better.
So, Are there times when one-hot encoding isn't the best approach?
Definitely. If fractional values, like 2.4, make sense in your data, one-hot encoding might lose that information.
How about that PyTorch code? What's that doing?
That code converts your scores into a one-hot encoding format usable by PyTorch. It's using a method called scatter_.
What does scatter_ do, and why is it important?
It modifies an existing tensor in place, instead of creating a new one. Scatter_ takes an existing tensor of scores, and places ones in columns corresponding to those scores in another new tensor.
That is key for memory efficiency. Can you explain the dot on squeeze one part?
We need that to make the target tensor compatible for scatter_. Unsqueeze adds a new dimension of size 1. This makes the tensor suitable for the scatter operation, ensuring it has the same number of dimensions.
So, it's ensuring the scores are properly positioned for the final encoding?
Exactly. It's like adding an extra layer of organization.
Okay, Samuel, we've talked about continuous and categorical data. Now, you mentioned ordinal data. How do we handle that in practice?
Yeah, ordinal data is tricky. There's no magic bullet.
So, no simple rule?
Exactly. Usually, it's treated like categorical data, losing the ordering information. Or it's treated as continuous, assigning arbitrary distances between values.
But why is that? Why can't we just keep the order?
Well, models might not learn the order if it's categorical. And if we treat it as continuous, we essentially create a distance between values. Like, how far apart is cold from cool? It's subjective.
So, it's a bit of a guess?
More of a trade-off. Sometimes, the model can pick up the ordering if you just have a few categories. But, sometimes we introduce an arbitrary notion of distance.
Interesting. So, in your example, you're treating weather like cold, cool, warm, hot as continuous data?
That's right. Because we're focusing on the numerical values. And if we had more categories like freezing, very cold, well, we might have to consider it more cautiously.
Got it. And what's the point of normalizing data like this?
Normalization helps the learning process. It makes all the features roughly the same scale. Kind of like, if you're working with weights and sizes for different kinds of things, scaling things will let the model focus on the differences better, which helps when you want to get accurate results.
I see. So, you're essentially standardizing the data, so the model doesn't get skewed by one feature being much larger or smaller than another.
Exactly. The numbers are important, not the absolute values.
You showed some code calculating the mean and variance of each column. Why are these numbers significant?
They tell us the average and spread of each chemical property. That allows us to see if one property is much more variable than another.
So, it's a way of looking at the data from a statistical perspective to understand which features are more impactful?
Exactly. The normalization step actually scales these values around a zero mean, essentially making it more convenient. This helps the training algorithm learn more effectively.
So, are there any pitfalls to watch out for when normalizing?
Definitely. If you don't understand the data's distribution, you can lose important information or introduce biases.
Okay, Samuel, so we're looking at wine quality now. You've identified a threshold for bad wines. Explain that process.
Right, Alfred. We're trying to find patterns, a way to quickly classify good wines from bad ones. We looked at wines scored 3 or lower. Those are our bad wines.
So, how do we identify these low-scoring wines?
We used a PyTorch function. It compares each wine score in a dataset with a threshold, and marks each wine as either bad or not bad. Think of it as a filter.
So, we're using a threshold, right?
Exactly. If a wine score is lower or equal to 3, it's flagged as bad.
Makes sense. And you found just 20 bad wines?
Precisely, Alfred. Out of the whole dataset. This shows there is some interesting work to do for improvement and better classification of wines.
Interesting. You then separated the bad wines from the whole dataset?
Correct. We grabbed all the details of just those 20 bad wines. Then we calculated average values for all the wine features for each category: bad, medium, good.
So, the average of each feature? Like acidity, sugar, etc.?
Exactly. We found differences in the averages across good, medium, and bad wines. For example, bad wines had higher total sulfur dioxide.
So, this suggests a correlation between total sulfur dioxide and wine quality, right?
Yes. The bad wines tended to have more of that. We found a midpoint, a threshold for total sulfur dioxide to distinguish potentially better wines.
So, now we have a threshold, total sulfur dioxide level. How did you decide on that threshold?
We found the average total sulfur dioxide level for the middling wines, which were scored 4 to 6.
And what did you do with that number?
Used it as a threshold. If the total sulfur dioxide level of a wine was lower than that midpoint, we flagged it as possibly high quality.
And you found that just over half of the wines fell below that threshold. That seems a bit surprising.
Well, that is the surprising part. The implication is that just over half of the wines fall below that threshold, but only 61% of the actually good wines fit that criterion.
So, it's not a perfect predictor. How did you figure out how good your threshold was?
We calculated what percentage of our predicted good wines were actually good.
So you compared your predicted good wines with the actual good wines.
Correct. It's not perfect. We found about 74% accuracy on our predicted good wines, but only 61% of the actual good wines were identified by our simple threshold method. It is only slightly better than random chance.
That shows why more than one factor is probably needed for better prediction. Thanks, Samuel. Now, what's the next step?
We need a more sophisticated method, like a neural network. That'll be covered in later chapters.
So, Samuel, we're moving from flat tables to time series data, right?
Yeah, exactly. Before, each row was independent. Now, order matters.
Makes sense. So, this bike sharing data, it's got time embedded in it, right?
Exactly. It's got hourly bike counts, weather, and stuff. Crucially, the data points are connected by time.
And this 3D thing, how does that work?
Well, imagine the flat table as a 2D grid. We add a third dimension, time. You get a 3D representation where one axis represents time of day, another is the day, and the other holds bike counts plus weather data.
So, it's like a stack of 2D tables, each for a different day, or hour, or?
Precisely. Each layer in the stack is a snapshot of the bike data at a given time. Very useful for understanding trends.
How does this differ from just looking at total daily bike counts?
It's way richer. You can see if bike usage surges at certain times of day or after certain weather events. This is important. It's crucial for pattern recognition.
So, time is a key variable now. That's cool.
It's vital. If you're trying to predict bike usage in the future, knowing the historical patterns is gold. You can see seasonal or even daily variations.
Can you give a simple example?
Sure. Maybe bike rentals spike before a work commute, or there's a drop in usage when it rains heavily. We can see these patterns in the data.
But how do you model it, like practically?
You'd use algorithms designed for time series data. We'd look for recurring patterns and seasonality, so we get a clearer understanding.
That sounds amazing. Any downsides?
Well, handling missing data is tricky, you know? In that dataset, if there's no rain data for a day, your analysis may be off, which could be a problem.
Okay, Samuel, so we're talking about this bike sharing dataset. You mentioned a time dimension. Explain how we're changing the data structure.
Yeah, right. Currently, each row is an hour's worth of data. We want to rearrange things.
Imagine a spreadsheet.
Instead of rows for every hour, we'll have a sequence of days.
So, one axis is for days, right?
Exactly. Another axis tracks the hours of the day, regardless of the date. And a third represents the different data points, weather, temperature, bike counts, and so on.
Got it. So, it's like stacking the data? Makes it easier to work with, right?
Precisely. Think of it like a 3D image. We're changing the perspective. Now we have a sequence of hours arranged within each day, essentially creating a time series that's easier to work with in a neural network.
How does this help with prediction? It's a key aspect of time series data, right?
Absolutely. Now we can see patterns and trends over time, like if it rained yesterday, did that affect today's bike rentals? By having a time dimension, we can capture those causal relationships and potentially predict future behavior. For instance, if there's a similar weather pattern today, We can forecast rentals based on previous data.
Interesting. So, our neural network will process these fixed-size chunks of data.
Exactly. We'll feed it a sequence of data. The size of each sequence, the chunk size, will be our channel size, essentially the column's worth of data. And there will be several parallel sequences from different days, effectively a time axis.
And those parallel sequences form the end dimension?
Yes, that's the time axis, 1 entry per hour. So the network sees patterns across several days' worth of hours. This allows us to detect subtle but significant changes in bike usage across time.
That's cool. So we're not just looking at 1 hour, but the preceding hours as well. That's how we capture those causal relationships you mentioned.
Yes, exactly. Now the network can learn those causal relationships, understanding that past weather events and patterns might influence future behavior.
Makes total sense. So, a sequence for a day's worth of bike rentals would be your chunk. How long should those sequences be?
The length depends on the problem, and you'll want to experiment with different lengths. Too short and you don't capture long-term patterns. Too long and your data will become difficult to analyze and the neural network might struggle to find relevant patterns.
Okay, Samuel, we're talking about reshaping time series data. So, we're breaking down a 2-year dataset into daily chunks. Why do we do this?
Well, Alfred, it's all about finding patterns. Imagine trying to predict bike sharing. Looking at hourly data, you might miss underlying daily trends. Chunking by days helps reveal those patterns. Think of it like zooming out on a map.
So, you're saying daily chunks are better than hourly?
Not necessarily better, just different. Hourly data is good, but daily chunks offer a different perspective. Think about your own schedule. You have daily rhythms, and that rhythm often influences your behavior. Likewise, we need different ways to analyze and discover such rhythms within our dataset.
Got it. This 24-hour chunk, is that just an arbitrary number?
No, it's a typical day. Plus, it depends on your data. If you had weekly patterns instead, you'd use 168 hours, or some other time frame. Crucially, the size of your dataset has to be compatible with the chunk size, i.e., the number of rows must be a multiple of 24 or 168 for this to work correctly. No gaps in the data, either.
Okay, and this bike's tensor you're using, what's the deal with that?
It's like a table of data. Think of a spreadsheet, but in Python. It's got 17,520 hours of bike sharing data across 17 different columns.
And then you reshape this to daily chunks?
Exactly. We use View to rearrange the data. View doesn't copy the data, it just reinterprets it. It's like looking at a deck of cards differently, not rearranging the cards themselves. Imagine each card as a data point. You don't need to shuffle the deck to see it differently.
So daily_bikes is now daily chunks, right?
Yes. It's got 730 days, 24 hours per day, and still 17 columns. Then we do another rearrangement using transpose to align our data precisely for our next steps in prediction modeling. This rearranges the columns, placing our hours in order and our columns in order. This step is crucial for our machine learning models, because it puts the data in a format our models can handle more effectively.
You mean we move from hours, then columns, to days, then columns?
That's right. This is how we restructure our data to work optimally with our deep learning models.
Wow, cool. So daily chunks are more manageable for prediction models because of that daily rhythm. But why is the stride important?
The stride tells us how much we move in memory to get to the next data point. It's important because it tells our models exactly how to access the data efficiently.
Okay, Samuel. So we're looking at transforming this weather situation variable. You mentioned one-hot encoding. Can you explain why that's a good choice here?
Sure, Alfred. One-hot encoding is great when you've got categorical data, like weather. It turns it into numerical data the neural network can understand.
Okay, but why not just treat it as a continuous variable? It's ordinal, right? One being good for being bad.
You could, but one-hot encoding often works better. If you treat it as continuous, the model might misinterpret the order. Imagine it giving more weight to a 3 than a 2. One-hot encoding avoids that by treating each level as a separate category. It's a lot clearer.
So, you're basically creating new columns for each weather type?
Exactly. Each category gets its own column, a 0 or a 1, to represent its presence. It's a powerful way to manage non-numerical data in a numerical format.
Got it. And this zero matrix, what exactly is that doing in the code?
It's a placeholder. We're creating a matrix of zeros, the same size as our bike data, ready to be filled with our one-hot encoding.
So, weather_hot, that's scatter. What's happening there?
That's where we place the ones. The index tells us exactly where to put them based on the value in the weather column. It's a very efficient way to change values in this matrix. It's like labeling the correct weather type in our new matrix.
Interesting. It sounds quite efficient. How do we join these two datasets together, then?
We use torch.cat. It stacks the original bike data columns with our new one-hot weather data columns. Crucially, the number of rows in both matrices needs to match.
Okay. So, this process is all for the first day's data?
Right. But we can do this for the entire dataset. We create a similar zero matrix, but we also adjust the number of columns in that matrix to represent all our weather options for each day. The core process remains the same. We just handle the whole dataset in chunks instead of just one.
Now you're talking about risk scaling. Why risk scale variables like temperature?
Neural networks often work better when all inputs are within a similar range. Risk scaling prevents certain variables from dominating, making sure the temperature has no more effect on the data than, say, the hour of day. It levels the playing field, so to speak.
So these two methods, min-max scaling and standardization, what's the difference?
Min-max scaling scales values to 0 to 1, while standardization centers the data around 0 with a standard deviation of 1. Each has its advantages, but standardization is better for handling outliers and maintaining the original distribution of a feature.
You mentioned other data types, like text and audio. How do we prepare those for machine learning models? Is it similar?
Similar in the sense of requiring transformations, but different in the techniques. Text needs tokenization and embedding techniques. Audio data often requires a series of steps depending on its structure and intended use. It's a whole different ballgame.
So, Samuel, you mentioned transformers. How are they different from RNNs?
RNNs, kind of process text sequentially. They look at one word, then the next, building up a picture. Transformers, though, can look at the whole sentence at once.
Whoa, that's different. How does that make a difference?
It's like, with RNNs, you miss context. A transformer can see all the words at once and understand the relationships between them better. It's like having a broader view.
So, better understanding. That's useful for what, exactly?
Think translation, summarization. But it's more than just that. Transformers handle complex relationships better.
You're saying they can understand the grammar of a language better from the data itself?
Exactly. Older methods used predefined rules. Transformers just learn from the data, which is kind of amazing.
So, simpler methods relied on explicit rules, right? While transformers are more data-driven?
Precisely. It's a huge shift. Think of a language model. Learning a language from a huge dataset, rather than being taught rules.
That's revolutionary. So, we're moving away from handcrafted rules.
Definitely. Deep learning is about letting the data speak for itself. You just feed it a ton of text.
And what about the translation part? How does that work with transformers?
The model learns the mappings between words and sentences in different languages by analyzing text.
So, PyTorch is a tool to help with this. Why is it useful?
PyTorch makes it easier to build and train these complex models. You can work with different types of neural networks efficiently.
So, in a nutshell, transformers let us learn about language directly from the data, and PyTorch helps us implement this?
That's the core idea. The tools give us the power. The data gives us the knowledge.
Cool. So, we're transforming text into numbers. Why is that important?
To feed it to neural networks, you need to represent text in a way the network can understand. Numbers, in this case.
Right. And what is this process called? Reshaping the data?
Yeah, that's right. We need to prepare the input.
Okay, Samuel. So we're talking text, right? Converting text to numbers. How does that work?
Yeah, Alfred. It's a crucial step. We need to turn words into something a computer can understand. It's like translating a language.
So, like one-hot encoding?
Exactly. Think of it like giving each letter or word a unique code, like assigning a specific number to each.
Right, like a dictionary. But how do we do this at a character level?
At the character level, every unique character gets a unique number. Simple, right? So a might be 1, be 2, and so on. It's essentially a lookup table.
So, if you had a phrase, how would this apply?
Say you have hello. Each letter would be assigned a number, H equals 1, E equals 2, L equals 3, O equals 4. The computer now understands hello as a sequence of numbers.
That's fascinating. So, we're making this huge conversion from language to something completely different?
Precisely. This transformation lets algorithms process text data.
And why is this important? Why not just use the words as they are?
Computers don't inherently understand words. We need this numerical representation for calculations and analysis. Think of searching, classifying, or even generating text, all relying on these numerical representations.
So, you're saying a text like Pride and Prejudice turns into a bunch of numbers?
Exactly. And that's not just true for characters. We can do this at the word level as well. Every unique word gets a number.
Okay. And that's why you mentioned that Project Gutenberg and Wikipedia corpus matter?
Absolutely. We need large amounts of text to train these models effectively. The more examples the model has, the better it gets. They help us get larger, more diverse datasets.
Interesting. So we're now ready to look at some code samples?
We can look at what steps are involved in loading a text file. We need to get text and prepare it for numerical conversion. It's just the initial steps, Alfred.
Okay, Samuel. So we're talking about one-hot encoding characters. This is crucial for feeding text into neural networks, right?
Exactly. Imagine a computer trying to understand language. It doesn't inherently know what A or Z means. It needs a numerical representation.
So, ASCII is a simple way to do that. Can you explain?
ASCII assigns a unique number to each character. A is 97, for example. It's pretty straightforward, but it only covers a limited set of characters.
So, what's the problem with ASCII?
It doesn't handle accents, special characters, or characters from other languages. That's why Unicode came along.
Ah, Unicode. So, it's a wider system.
It's a standard that assigns numbers to all known characters. Then encodings like UTF-8, UTF-16, and UTF-32 define how to represent those numbers using bits.
Gotcha. So, why are we talking about one-hot encoding specifically in this context?
We're transforming these characters into a format neural networks understand. One-hot encoding gives each character a unique, binary vector representation.
Like, is a bunch of zeros and one?
Exactly. The vector has a length equal to the total number of different characters in our encoding. The 1 sits at the index that corresponds to the character's number. That's how our neural net can interpret it.
And you mentioned limiting the encoding. Why?
If we use too many characters, the vectors get gigantic. We often filter out punctuation or numbers. In this case, English text, we can probably stick to ASCII and make it lowercase. That cuts down on the encoding size.
Okay, so we're creating a big vector of all zeros except one?
We create a tensor. It's like a matrix of these binary vectors, one for each character in the line.
And the code shows how that tensor is built, right?
Yes, it shows how we create a tensor that's long enough to hold one-hot vectors for each character in the line. Then we iterate through the characters and put a 1 at the correct position in the vector for each character.
What if we find an out-of-range character?
The code handles that. If a character's numerical value is beyond our encoding's limit, it sets it to 0. That means the character gets ignored in the one-hot encoding.
Clever. This helps to train neural networks using text data, correct?
Absolutely. It turns unstructured text into something the network can understand. It's a key step in many NLP applications. We just have to be mindful of character limitations within the specific dataset used.
Okay, Samuel, so we've one-hot encoded sentences. But you mentioned word-level encoding is tricky. Why?
Yeah, one-hot encoding words is possible, but it creates huge vectors. Imagine a vocabulary with thousands of words. That's a super wide vector. It becomes impractical for a neural network.
So, a wide vector is bad?
Exactly. It's inefficient. And remember, neural networks like compact, manageable representations.
Right. So, we need a more efficient way?
Absolutely. The next step is word embeddings, which we'll talk about later. But for now, let's stick with one-hot encoding. You see how we clean up the words first?
Yeah, by stripping punctuation, converting to lowercase, etc.
That cleaning step's crucial for accuracy. And then we build this mapping.
This word-to-index dictionary. How does it help?
It gives each word a unique number. It's a quick way to look up a word's position in the encoding.
So, practical example?
Sure, in the code example, we take that sentence, break it down into words, and then use that mapping to create this special one-hot vector for each word. This vector has a 1 in the position of the word's index. A lot of zeros otherwise.
So, each word now has a specific position in this one-hot encoding. Is this still just a simple replacement?
Yes, but it's now numerical, so the neural network can understand it.
That's pretty neat. This one-hot encoding, is it the final form the text is in for processing?
No, it's just one intermediate representation. It's a stepping stone to a more refined form of representation. This approach shows the difference between character-level and word-level encoding.
So, why do we use character-level versus word-level?
You know, it's a trade-off. Fewer characters, easier to represent, but it often captures less meaning. A word has more meaning than its characters. Words are much more informative.
So word-level encoding is often preferred?
Usually, yes. But there are methods like byte-pair encoding that aim to bridge that gap. It starts with characters but builds up a dictionary of more meaningful word-like tokens as it goes. Kind of a smart combination of character and word representations.
Fascinating, Samuel. I see how it's a crucial step in text processing. This is shaping up to be a much deeper process than I thought. So, Samuel, we've talked about one-hot encoding, which, as you pointed out, has limitations. What exactly are these limitations?
Yeah, one-hot gets unwieldy fast. Imagine representing every single word in a book. You're talking about thousands, maybe tens of thousands of features. And every new word means a whole new column, making training a real pain.
Right. That's a huge problem. So, how does embedding solve this issue?
Embeddings compress that information. Instead of a long list of zeros and a single one, you use floating point numbers. Think of a 100-dimensional space. Each word gets a unique point in that space.
A point in a 100-dimensional space? That sounds complex. Can you give me a simpler example?
Absolutely. Picture a simple 2D graph, like the one in the figure. You've got fruit words here, color words there. Each word gets coordinates. Apple would be near fruit and red.
So, words with similar meanings end up near each other?
Exactly. Apple and orange are close, apple and banana are closer than apple and car. This representation captures relationships, unlike the scattered one-hot approach.
That makes sense. But how do we generate these embeddings?
Well, you could, in theory, randomly place each word. But that loses all meaning. Ideally, similar words are near each other. A human could manually position words. We'd assign coordinates to words like fruit and red to set the initial groundwork for the embedding.
So, you're saying we place words based on their meaning?
Precisely. And in a real situation, you're not using just 2 dimensions. It's a much higher dimensional space. But the idea of arranging words in a meaningful contextual relationship remains the same.
And how is this done automatically?
Computers can do it. By feeding a massive text corpus into a neural network, it learns to predict words from their context. It essentially figures out the relationship between words, and creates the embeddings based on that learned relationship.
That sounds quite powerful. Can you see how this would work in a search engine, for example?
Definitely. A search engine could use these embeddings to find similar documents. The query would have an embedding, and the engine would look for documents with similar embeddings.
And if a new word appears, how does the embedding handle that?
The model continues to learn, adjusting the embeddings to maintain context and relationships with existing words. So it adapts over time.
This whole process is very cool. So, embeddings capture meaning and relationships, helping us with more powerful models, right?
Absolutely. And as the example shows, you can perform analogies on the word vectors themselves. Like apple red plus yellow might lead to something like lemon.
So, Samuel, embeddings, right? They're a big deal. Why are they so crucial?
Yeah, absolutely. Imagine you have tons of words. Representing them with just a bunch of zeros and ones gets messy, right? One hot in coding. Embeddings? They're a numeric shortcut.
A shortcut? Like a map?
Precisely. These numbers capture relationships between words. It's not just a number for each word, it's a compressed representation.
So, they're like a simplified language?
Think of it as a smarter way to represent categories. It's way more efficient than one hot, especially when you need to do calculations or find similar words.
Okay, so they help with large vocabularies?
Exactly. And not just words. Categorical data in general. Any situation where one hot encoding is a pain.
But how are these embeddings created?
Well, sometimes they're pre-built. Like for words. But in other domains, you can't use pre-made embeddings, so we might have to learn them.
Learn them? Like training a model?
Exactly. We can use existing data, that's the cool thing, to find better numbers for these categories. And that learning process can be part of the whole process.
Wait, so we're adjusting these embeddings while also trying to solve the problem?
Yep. Very common now, even in text. And you can even build upon what others have already learned with text embedding, and adapt them.
This is powerful. So, you're saying that these embeddings can be like a blueprint for other tasks, right?
Absolutely. If you're looking for patterns between users, like customers who bought one book also bought another, you can apply ideas from word embeddings.
Like in recommender systems?
Exactly. Using prior behavior as a context. And look at time series analysis, too. So much can be learned from how we work with text sequences.
That's interesting. So if we understand embeddings well, we can tackle many different problems?
Yes, it's a transferable skill. Embeddings show us that.
So, we've covered a lot of data formats. Any surprising gaps?
Well, some formats are complex, like medical records. Others, like audio and video, are less common for this book's focus.
Right. But you mentioned bonus material. What's the deal with that?
Yeah, extra Jupyter notebooks have audio and video tensor examples. They're on the website and GitHub.
Cool. So, now we move to training neural networks? That's the goal?
Exactly. Next chapter tackles training simple linear models.
Linear models? Simple? How can that be relevant?
They're foundational. Understanding how they learn is crucial to complex network training.
Can you give an example, like why it's needed?
Sure. Imagine predicting house prices. A linear model could be a great starting point, showing how different factors affect price.
So it's a stepping stone?
Absolutely. It sets the stage for more intricate neural networks later.
Interesting. So, we're not just dealing with data anymore? It's about learning now?
Precisely. We're going from data representation to algorithms that learn from that data.